So let's collect 3 lemmas. And first, we need a lemma which can collect the vertices which has an edge to previous one, and then this together dominates lots of vertices here. And then we also need another lemma which, by adding some vertices, we can make this connected. Then you take this and you pull it up, then you get a connected graph which dominates lots of vertices in here and which has edges into previous one. So we need lemma regarding choosing the vertices which dominates the other vertices, and we need a lemma which regarding that we can make the given vertex set, we can add some vertices so that the result is a connected graph. So let's prove this first lemma. Let G be an m vertex graph with minimum degree high, which is a bit bigger than half of the number of vertices. So this is motivated because later we will take this minor of G, satisfying the condition that each vertex has degree, minimum degree is bigger than half of the number of vertices. So with this, say if S is smaller than n minus 3, and let X be a subset of graph, the vertex of graph, then what we want to show is there are S plus 3 vertices of G such that each of the vertex dominates at least half of the vertices in X. So that's what we want to prove. For a given set X, we can find several vertices which sends edges at least half there. So this will be useful for us. Let's prove this. Let's say the X has exactly k vertices and T with a set of vertices which dominates at least half of the vertices in X. That's the vertex that we are interested in. Suppose we don't have enough, so T is at most S plus 2. Then we would get a contradiction because let's say S is a pair of vertex X and V such that X is in this capital X and V is arbitrary vertex in G, so that XV is not an edge. Then what do you get? The size of S is at most for each vertex X. So there are k vertex S, and each of the vertex has at most this many non-neighbor. So there are n-1 other vertices. Out of that, at least delta many, the minimum degree, many of them are neighbors and rest of them can be non-neighbor, so we get this upper bound. And this is at most half times k times n plus s minus 2, based on this assumption that minimum degree is at least half times n plus s. You plug in here, then you get this. On the other hand, we can prove the lower bound in S. So it's double counting. So this is counted from the perspective of X, and now perspective of V. For each V which is not in T, if V is not in T, then it has at least, more than this many non-neighbors in X. So you can add half times k plus 1, many choice of X, where V and X are not adjacent and X lies in X, S lies in capital X. And what's this? You just assume that the T has size smaller than S plus 2. So you can add up all vertices not in S, which is m minus s minus 2 at least. And each time you take half k plus 1. So you compare these two. But you get that this is bigger than this, right? So S is smaller than that, but S is bigger than that, which is a contradiction. So this proves this lemma. And let's use this. We can prove this lemma. So now what we are interested in is that later we have x1, x2, x3, and then they dominate lots of vertices. And then now we want to choose the set which dominates lots of vertices inside, as well as there are edges between these two other. So in order to do that, we are interested in how many set of certain size dominates many vertices here. And if you can compute the number, then you write down the number, and then you compute the numbers of the set which doesn't contain any vertex which is dominated by x1. So there are certain number of bad sets which doesn't have any edges to x1. And you can also count the bad sets which doesn't have edges to x2, which doesn't have edges to x3, and that number is smaller than the, this previous number of sets which dominates a lot. Then we can find the set which dominates lots of vertices here and have edges to all previous one. So that for that purpose, we are interested in how many sets are there which dominates lots of vertices. So let G be an n vertex graph. With, again, minimum degree at least, say, n plus s over 2 for s and most n minus 3. Then there are at least s plus 3 choose k many sets of size k, such that each set dominates many vertices in G, meaning all except 2 to the minus kn vertices of G. So how we will prove it? We use induction on K. And if K is 0, then there is nothing to prove. Because we want to find the sets which dominates all but all vertices. So there is no condition. As long as you find one, vertex, that's good. No, even the K is 0, so we want to find the empty set. Empty set vacuously satisfy this. So assume that there are S plus 3 choose K minus 1 subsets of size K minus 1, which dominates all but 2 to the minus K plus 1 and vertices of G. So that's our induction hypothesis. We know that there are that many. So let Y be one such, say, K minus 1 set, meaning the set of size K minus 1. And let X be the set of vertices not dominated by Y. So you have Y and you have X. So there are things that rest of them is dominated, X is not. Now what we want to find is that Y is K minus 1 set. So we want to find many K set which dominates many vertices. So we want to add one more vertex here to Y to get a bigger set of size K. But now what we want is that before the non-dominating size was 2 to the minus K times N. But now it wants to dominate at least half more from X. Then remaining thing gets smaller by half. And the previous lemma give you that there are at least certain number of vertices which satisfy that. So whenever you add this vertex to Y, you get a set that we want. So for that, we just first note that this X has this many sizes. And the previous lemma implies that there are S minus K plus 4 vertices of G minus Y, because now we want to choose these vertices outside of Y. So we delete Y, then previously we have this condition, and we delete Y. Y has K minus 1 vertices. So number of vertices is N minus K plus 1. And then minimum degree in G minus Y is at least half times N plus S minus K plus 1, which is at least 2 times N minus K plus 1 plus half times S minus K plus 1. Wait, is it correct? Let me see. N plus S minus K. Yeah. So this is our, this is our S in the previous theorem, while this is our N. So that plus 3 is this number. So we get this many vertices of G minus Y dominating at least half of the vertices in X. So adding any of these vertices to Y forms a desired K subset of size K. So that gives us lots of subsets of size K, because each of this Y can be chosen out from this many subsets. But that doesn't directly give you the answer, because some sets of size K could be counted more than once. For example, if we have this set of size K, but this could come from this Y plus this one vertex, or this Y plus this one vertex, or this Y plus this one vertex. Then it's counted several times. But it can be counted at most K times, right? This K set can be formed in at most exactly K ways by the, I wouldn't say exactly, but at most by addition of a vertex to a K-1 subset, which is one of these subsets dominating a lot. So the number of our desired K subset is at least, so S plus 3 choose K-1 set. Each time we extend it by choosing this many vertices, but we have to divide it by K, because same set can be counted up to K times. Then this is actually S plus 3 choose K. So this finishes the induction. So now we find this many sets of size K, which dominates all but 2 to the minus K times n vertices of G. So this proves this lemma. So this lemma is what we will use regarding the finding vertex sets which dominates lots of vertices. And now we want to prove some lemma which can turns a set into another set by adding some more, so that the resulting set induces a connected graph in G. So let's say lemma 5.18. Let G be an n-vertex graph with, again, minimum degree more than half times n plus some number. Let's say log sub 2 of K for some K, and let W be a subset of size K. Then there is a subset U of vertex set which has size at most 2 times the log sub 2K plus 1 with floor, such that W together with U induces a connected graph in G. So let's use induction. If K is 1, then nothing to prove. Because empty U taking as a empty U as an empty set already works. So assume K at least 2. So by the previous lemma 5.16, we can find there exists a vertex Y which dominating at least half vertices. Of W. So 5.16 says that, you can find some vertices dominating half of that as long as this S is non-trivial. So K is at least 1, K is at least 2 there, so we can, apply that with S at least 1. So you have W, and then half of the vertices, you can find the Y, which is connected to half of them, at least. Now you consider this. Now you consider the remaining half of the W. So let G prime be G minus Y, and let W prime be the vertices not dominated by Y. Then we know that this W prime has size at most K minus 2, and this minimum degree of G prime is because we delete one vertex. This is half times n plus log 2 K minus 1. So it also lowers by 1. So you can actually show that this is half times n minus 1, which is the number of vertices, plus log 2 size of W. So by induction hypothesis, there exists a subset U prime of G prime of size 2 times log K floor minus 1 many, such that W prime union with U prime induces a connected subgraph. So now we are almost done. We choose Y prime in, say, U prime. So you have the W. So Y is here. Y. So you have U prime. So here Y prime. And they are somehow connected. And Y and Y prime has both has in graph G degree at least n over 2. So either they are adjacent, or they have a common neighbor. W. Then we let the U as a U prime intersection, union with W and Y. Then this forms a desired set. Now because these are connected and this is connected and you add this, so everything is connected, and the size is from here, and you add at most 2 more vertices, so the size is at most this number. So this proves this lemma. So we collected these 3 lemmas, and we will use this to prove this Kosochka-Thomason theorem in the next time. So this shows that if we have a large average degree, then we can find the complete graph minor, KT minor.